Okay, we're going to look at solving systems of equations with matrices. And so we're going to look at two main methods, the Guassian Elimination and the Guass-Jordan Elimination method. But before we can do this, we need to view how to, what matrices are. So a matrix is a rectangular array of real numbers. The order of the matrix is determined by the number of rows times the number of columns. There are a couple special names of matrices. A matrices with only one row is called a row matrix. A matrix with only one column is called a column matrix. So for the next few examples, we're going to determine the order of each matrix. Okay, first you look at the number of rows, which is 1, and the number of columns is 1. So this is a 1 by 1 matrix. And for example B, there is again 1 row, but there are 4 columns. So this is a 1 by 4 matrix. Okay, your turn. For example A here, we have 2 rows and 2 columns, so this is a 2 by 2 matrix. And for example B, we have 3 rows and 2 columns, so this is a 3 by 2 matrix. Now notice on both example A's that I had up here, we have what's called a square matrix. When the number of rows equals the number of columns, it has a special name, it's called a square matrix. Okay. Now we're going to look at using matrices to solve systems of equation. A matrix derived from a system of linear equations, each written in standard form with the constant term on the right, is called an augmented matrix of the system. The matrix derived from the coefficients of the system, but not including the constant term, is the coefficient matrix of the system. We'll be using augmented matrix to solve systems today, but in future techniques, we'll use what's called the coefficient matrix. So let's look at how to write this. Now, first thing we have to do is, the key is, in order to write an augmented matrix, the system has to be in standard form. So we have to have our variables in order. And here we have 4 variables, x, y, z, and w. We write it in form of the x term, the y term, the z term, and the w. Now, what I'm doing right now is I'm just separating these so I can get all the x terms in one column, one kind of group together, then all the y's, all the z's, and all the w's. Because when I write my augmented matrix in the next step, the first column is going to be all the x's. Second column is the y coefficients. Third column is the z coefficients. And the fourth column will be the w coefficients. And then the last column will be our constant term. So here I'm labeling the columns. Now you do not label the columns when you actually do these. And then each row is determined by each equation. So the first row is the coefficients of all the first equation. And then second row, coefficients of the second equation, etc. Now, if a variable doesn't appear in an equation, we have to put in a placeholder of 0. So let's look at the first equation here. X plus 3y minus w equals 9. So coefficient of x is 1, coefficient of y is 3, coefficient of z is not there, so we put in a 0. And then the -1 for w, and the answer is y. Now notice that to separate an augmented matrix, the coefficients of the equation with from the constant term, we do these 3 little dots. That's sort of like the equal sign when in our augmented matrix. And that's how we note that equal sign. And then our last one will be 2, 4, -3, 0, and ... 4. This is how you write an augmented matrix from a system of equations. Again, the labeling of the rows and columns you will not put. So just this part would be your answer. So the order of this matrix is a 4 by 5. A coefficient matrix for the system is just the left-hand side, disregarding the equal to the constant. So our coefficient matrix would be 1, 3, 0, -1, 0, -1, 4, 2, 1, 0, -5, 6, and 2, 4, -3, 0. So again, this order here is a 4 by 4. So that's the difference between an augmented matrix and a coefficient matrix. Now that we can make a matrix from a system of equations, we need to look at what we can do with that matrix. And when you're working within a single matrix, you have 3 elementary row operations that you can perform. These are the only 3 things that you can do within one matrix. The first elementary row operation is to interchange 2 rows. So we can change 2 rows in the order in which they're written. So we can make row A interchange with row B, and that's the notation that we'll put to show the reader what we're doing. The second elementary row operation is to multiply a row by a constant, and that constant can be any number except 0. I'll abbreviate the constant as a C, so I can take a constant times row A. And our last elementary row operations is that we can add a multiple of a row to another row. For example, that would be constant times row A plus row B would be our notation for that. Okay, next information that you need to know to perform our first operation is something called row echelon form of a matrix. Okay, a matrix will be in row echelon form if it has the following four properties. The first property, if you have any rows consisting entirely of zeros, they occur at the bottom of the matrix. So all row zeros have to be at the very end of the matrix. For each row that does not consist entirely of zero, the first non-zero entry is a 1. This is called the leading one. And that's like one of our steps in our system is get the leading ones first. For two consecutive non-zero rows, the leading one in the higher row is further to the left than the leading one in a lower row. And then finally, a matrix in row echelon form will be in reduced row echelon form. That's the second type of form that you can do, when every column that has a leading one has 0 in every position above and below its leading one. Okay, so now let's just learn to recognize row echelon form, if it is or if it's not. So in example A, we're looking to see if this is in row echelon form. So we're looking at those four characteristics are met. Okay, if it is, then we're going to look and see if it's also in reduced row echelon form. So I have a leading one, but then I have a row of all zeros, and that row of all zeros is not at the bottom, so this is not in row echelon form. Okay, looking at example B, we have a leading one in the first row. Then we have a 0 followed by a leading 1. So our first non-zero entry is 1. So that one's good. And the third row that occurs in the last row is all zeros. So yes, this one is in row echelon form. It is not reduced row echelon form because we do not have zeros above our leading ones. Okay, example C, first row we have a leading 1 and then second row our first entry is a leading 1, third row our first entry is a leading 1, and fourth row our first entry is a leading 1. This is in row echelon form. It is not reduced row echelon form, again, because we do not have zeros in all entries above each leading one. Your turn. Okay, in the second row, our first entry is not a 1. The non-zero entry is not a 1, so this is not in row echelon form. And that is because our first entry in row 2 is not a leading 1. Our last example, our first row has a leading 1, the second row has a leading 1, and all zeros are in our last row. So this is row echelon form, but notice that for each leading 1 term, we have 0 entries above and below it, and all other entries in that column are zeros. And so this is an example of a reduced row echelon form. Now that we have this background information, we're finally ready to learn our first system of equations. The full name is called the Guassian Elimination with back substitution, usually just called Guassian Elimination for short. Now, in order to do this method, the first thing you're going to do is you're going to give a system of equation, and you're going to write the system, you're going to write the augmented matrix for that system of equations. So step 1, convert the system of equation into an augmented matrix. Then you're going to use any of the 3 elementary row operations that we've learned to rewrite the augmented matrix into row echelon form. My hint to you, in the process of writing this into row echelon form, you should operate from the left to right by columns to obtain your leading ones in all entries, to obtain zeros in all entries directly below your leading ones. So you step 1, you're going to find your leading 1 and then find all zeros in that column below it. Then your next column, go to your leading 1 and then find all zeros below it. And then move to your third column, get your leading 1, and then find all zeros below it, etc. So that's kind of the process that you're going to go through to rewrite each augmented matrix into a row echelon form. Make sure in order to get it into augmented matrix into row echelon form, you work by column. Now that you have it in row echelon form, you're going to convert that row echelon form back into a system of equation, putting the variables back in, and then you're going to solve this system by using back substitution. I'll show you an example as you go through this. But remember, as we've done in our systems and previous techniques, you may have a system that has no solution. How you identify no solution by an augmented matrix or a row echelon matrix that has no solution is if you attain a row with all zeros except for the last entry, which is your coefficient, that if that coefficient is not 0, therefore you have a false statement and your system is inconsistent. All right, so let's work through our first Guassian elimination with back substitution. So for step 1, I want you to write the augmented matrix to this matrix. Please pause and try that. Okay, so again, our first column is going to be x's, second column y's, third column z's, and fourth column w's, dot, 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 our coefficient column. So for row 1, that'd be 0, 1, 1, negative 2, and negative 3. For row 2, that'd be 1, 2, negative 1, 0, and 2. Repeat this for equations 3 and 4. Okay, now that I have an augmented matrix, our next step is to get this into row echelon form. So we need to start by having a leading 1 in the very first row, first entry. But notice we have a 0 there instead. So that first equation is not going to work in this position. We need a leading 1 here. And so I'm going to do my elementary row operation where I'm going to switch my entries, my row 1s and row 2. So over to the side, it's very important that you describe your techniques over to the side with correct notation. So I'm interchanging row 1 and row 2. So in my first, I'm copying down my row 1, my row 2 into row 1 spot and row 1 into row 2 spot. Now notice my row 3 and row 4 are staying the same, so I just copy it down. All right, so that's our first step. We have now our leading 1 in our first column. So our next goal is to get zeros in all entries below that leading 1. The second row already has a 0, so we don't mess with that. So now we need to figure out a way to get a 0 in place of the 2 in the third row and a 1 in the fourth row. Now, how you do this, I always go back to my leading 1 row. So row 1 has my leading 1 for column 1. And so that's the one I'm going to work with. Now, since row 2 already has that 0, I'm not going to do anything for it, so I can copy it down. Now I'm going to move to my row 3. Now, what can I do to make a 2 a 0? Well, I could do our third elementary row operation. If I multiply row 1 by negative 2, and I add that to my row 3, that'll give me my new row 3. This is how I note that. All right, so negative 2 times 1 is negative 2. Negative 2 plus 2, I'm looking at my previous matrix to figure out my rows here, gives me a 0. And then negative 2 times 2 plus 4 gives me 0. Negative 2 times negative 1 is 1. 1 plus 1, negative 2 plus 1 is 3. And then gives me a negative 3. And then negative 4 minus 2 gives me a negative 6. I also need a 0 in this first entry of my last row. So I'm going to do, again, the same thing, but this time I'm going to multiply row 1 by negative 1 and add it to row 4 to get my new row 4. I have now completed my first column. I have a leading 1 followed by all zeros in that column. So my next goal is to move to row 2. So now I'm looking at my second row, first column, and making that a leading 1. It's already a leading 1, so I don't have to do that step. So that means now below that leading 1, I need all zeros. So the only one that's not a 0 is my row 4. So I'm only going to be working with row 4. So I'm going to copy down row 1, 2, and 3 will be the same as the last matrix. And then for row 4, I need to do an elementary row operation so that I can make that negative 6 a 0. And the way I can do that is I can multiply my leading 1, which is in row 2, by 6 and add that to my row 4. So 6 times row 2 plus row 4 yields my new row 4. Doing that, I get 0, 0, 0, negative 13, and negative 39. So first column is done, second column's done. Now I'm moving to the third column. So again, in the third column, I need a leading 1, but this time I don't have a leading 1 already. So my next matrix is going to be making our leading 1 in that third row. Now, how I can do that is a new elementary row operation. I can multiply that row by a single coefficient. I'm going to choose the coefficient to be 1/3 or 3. So if I multiply row 3 by 1/3, I will get my leading 1, because 1/3 of 3 is 1. And then I'm not doing anything with row 4, so just copy it down as it is. And I now have my first column fixed. I have my leading 1 with all zeros below it. My second column, I got my leading 1 with all zeros below it. And my third column, I got a leading 1 with all zeros below it. I'm almost into row echelon form. The only thing left is that last column needs to have a leading 1. So how can I get a leading 1 in this position of negative 13? Well, again, do our elementary row operation by multiplying by a constant. I'm going to choose that constant to be negative 1 over 13, so I can get a 1 in that leading 1 position. So again, our operation here is I'm going to take negative 1/13 R4 to get our new R4, row 4. Now we've successfully written this into row echelon form. That was our first step into solving these matrices. Now that I have it in row echelon form, our next step is to put the variables back in. So I'm going to rewrite this as a system equation, putting the variables back in. Let me give myself some more room. So row 1 would translate to x plus 2y minus z equals 2. Row 2 would translate to y plus z minus 2w equals negative 3. In row 3, I just got a z minus a w equals a negative 2. In row 4, I got w equals 3. So this is our new system of equations. Now that we have our system equation, we're going to do something called back substitution. So we are ready to do this back substitution. We start at the bottom, the last equation. We got that w is equal to 3. So we already figure out what our w value is. So we're going to move up one equation, go back to one equation. And now we have z minus w is equal to negative 2. Solving that equation, replacing w with 3, and solving that equation, we get z is equal to 1. Then we're going to go back to the next equation, y plus z minus 2w equals negative 3. We place every w with 3 and every z with 1. And solve for y. We get that y is equal to 2. And then we're going to go back to the next equation, replacing every y with 2, z with 1, and w with 3. And solving for x. And we get x is equal to negative 1. So our solution is negative 1, 2, 1, and 3. We write this in the order of x, y, z, then w. And that's how you solve a system equation using Guass-Jordan elimination. You try this one. First step, write the augmented matrix to this system. Okay, we're going to look at solving this system and see how you did. So first, let's see your augmented matrix that you wrote. Should be 1, 1, negative 1, and 7. 1, 0, 1, and 2. Third row is 2, 4, negative 1, and 10. And the last row is 1, negative 1, 4, and negative 5. Next, you need a leading 1 in first entry, first row, which we already have. So we don't have to worry about that. And once you have that leading 1, your next goal is to get all zeros in the entries below. So that's what we'll do in the next matrix. So since my leading 1 is row 1, I'm just going to copy it down. I'm not going to change it. Okay, I can multiply row 1 by negative 1 and add it to row 2, and that'll give me my new row 2 that I'll be writing. So looking at my previous matrix, I'm going to take my row 1 and times it by negative 1 and add row 2. For the third row, I'm going to take negative 2 times it by row 1 and then add row 3 for my new row 3. So negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 1 is negative 2 plus 4 is 2. Negative 2 times negative 2 is 2 minus 1 is 1. And negative 14 plus 10 is negative 4. For my last row, I'm going to take a negative 1 times row 1 and add it to row 4 to get new row 4. So negative 1 plus 1 is 0. Negative 1 minus 1 is negative 2. 1 plus 4 is 5. And negative 7 plus a negative 5 is negative 12. So my first column is complete. I have my leading 1, followed by zeros, all the zeros and entries below it in that column. So step 2 is to get a leading 1 in my second row, second entry. Easiest way to get a leading 1 in this spot is to simply to multiply my row 2 by a negative 1. So in this matrix, I have successfully got my second leading 1. So my next goal for the next matrix is to get zeros in all entries below my leading 1. So I'm going to copy down my rows 1 and 2 as is, and then I'm going to use my row 2 and elementary row operations to eliminate, to make my my orange highlights into zeros. To do this, I'm going to multiply my row 2 by negative 2 and add it to my row 3 to get my new row 3. So 0 times negative 2 is 0 plus 0. And then negative 2 plus 2 is 0. 4 plus 1 is 5. And negative 10 plus a negative 4 is negative 14. And then if I multiply row 2 by 2 and add it to row 4, I get my new row 4. So that would be 0 plus 0. 2 minus 2. 4 plus 5, negative 4 plus 5 is 1, and then 10 minus 12 is negative 2. All right, so my second column is complete. So for my first column, I have my leading ones for column 1 and column 2. I have my zeros underneath my leading ones in those two columns. So next go is to get a leading one in my third entry of my third row. I'm going to choose to do this by interchanging my rows 3 and rows 4. So I'm going to not work with rows 1 and 2, so I'll just copy those down. And now I'll interchange my rows 3 and row 4. I have now successfully found all my leading ones. So my final goal is to get a 0 in the entry underneath this last leading one. I can do that by simply multiplying my row 3 by negative 5 and adding it to row 4. And so that's what I'll do in this last matrix. All right, success. I now have this matrix in reduced row echelon form. I have my leading ones that are along the diagonal, and below each leading one, I have entries of 0. So this is in row echelon form. Before I tried doing back substitution, or when I try to do back substitution here, I have an error. I have a problem with this bottom row, because notice I have 0 equal to negative 4, and that is a false statement. Recall that anytime you have a false statement, the answer to this system is no solution. So I can stop. I don't actually have to do the back substitution to this problem. So now we're going to learn our next technique called the Guass-Jordan Elimination method. So this is going to start with the same as the Guassian Elimination method. You're going to rewrite your system and as an augmented matrix. Then you're going to perform your elementary row operations, but this time we're going to write the augmented matrix into reduced row echelon form. So instead of, we're going to get it all the way down to reduced row echelon form. And then from that, you should go straight to finding your solutions. You will not need to do any back substitution. So we're going to solve this system using the Guass-Jordan Elimination method. So find your augmented matrix. Okay, so now that I have my augmented matrix, I'm going to get my leading one in my first column, first entry, which I already have. And so my next step is to get all zeros in the entries below that. So column 1 should be 1, 0, 0. So to get 0 in this second row, I'm going to multiply row 1. I'm just going to add row 1 and row 2 together to get my new row 2. And to get a 0 in row 3, I'm going to take negative 2 times row 1 plus row 3 to get my new row 3. All right, now I need a leading 1 in my next entry, which I already have. And so now I'm going to get a 0 in the entry below it. And I can do that by taking row 2 and adding it to row 3 to get my new row 3. Okay, and now I need a leading 1 in my third column, and so I can just multiply row 3 by 1/2 to get a 1 in that entry. Now, if I had been solving this using the Guassian Elimination method, I would be done with the matrices and I would convert it to a system. But since we are not, we're using the Guass-Jordan method, I need to get this into row echelon form now. So I'm going to go back to column 2, and I'm going to need to get a 0 in that entry above my leading 1. So how can I get a 0 in that entry above my leading 1? Simple. I can multiply my leading 1 row, which is row 2 by 2, and add it to row 1 to get my new row 1. Now this step you could have done with the previous matrix. Once you get your leading 1 in that column 1, you can get all the zeros in that row. So I could have done this with my last step if you want to combine them. Or you can just simply always get into row echelon form and then do reduce row echelon form, whichever way works best. Okay, now looking at my my leading 1 in my third column, I need to get all zeros in that last entry. So I'm working with row 3. So to get 9 to become 0, I need to take negative 9 times row 3 and add that to row 1 to get my new row 1. And then I'll take a negative 3 times row 3 and add that to row 2 to get my new row 2. To get 0, 1, 0, negative 1. So now I have this in reduced row echelon form. Now what's great about reduced row echelon form, notice my first column is my x's, so this first row says x equals 1. My second row says y is equal to negative 1. And my third row says that z is equal to 2. So I've solved the system. My solution is 1, 1, 2. Okay, we're going to solve this next equation by using the Guass-Jordan Elimination method as well. Okay, so we're going to find our augmented matrix. Okay, now we need a leading one in our first entry of our first row. I can easily get that by interchanging my row 1 and row 3. My next step is to get underneath that leading one in that first column to get all zeros in my the rest of that column, so please do that. You got the 0 in your row 2 by taking row 1 and adding it to row 2 to get your new row 2. And we can get our 0 in column 1 by multiplying our row 1 by -3 and adding it to row 3 to get our new row 3. Okay, now I need a leading one in my second column, second entry, and I can do that by interchanging my row 1 and row 3. Alright, now I need my leading one in my third row. So I need a leading one in third row. I can do that by multiplying row 3 by -1/3, the -1/2. So we are in row echelon form, so now we need to get into reduced row echelon form. So in column 2, get a 0 in our second entry, and I can do that by taking row 1 plus row 2. And last step is I need to get zeros in that third column above every leading one, above the leading one. So I can do that by taking -9 times my row 3 and adding that to my row 1. And then for my row 2, I can take -13 row 3 and add that to row 2 to get my new row 2. And my row 3, I just copy down as is. So now I have it in reduced row echelon form, so I can solve. X is 5, Y is -1, Z is -2. Solution is 5, -1, -2. And that's how you solve system of equation using the Guassian Jordan elimination method.